what I'll do is I'll be annotating this and drawing on the PowerPoint. At the end of lecture, I'll save it and then I'll post it. So you'll have the PowerPoint after class, okay? And so all I ask is, again, give me your thoughts on whether this is better than using the Blackboard. When I did this 4 years ago, the students hated the PowerPoint. They liked the Blackboard better, but that was pre-online. So you can see these announcements. Lab 2 is now posted, due 4 p.m. Friday a week from today. If you have any questions about which lab group you enrolled, again, we posted those all in Canvas a day or two ago. Make sure your name is in the lab group if you are enrolled in the lab. Not all students have to take the lab. They gave me a really big fat bribe, so they're not taking it. So we're on, hopefully, the last lecture on fluid properties. I may or may not finish this today. And for the fluid properties, we've already talked about density, specifically, specific gravity. And then last time we talked about viscosity, dynamic viscosity, kinematic viscosity. And you can see the letters we're going to be using for the rest of this course for these properties and their FLT dimension. And again, they're all in the back of your book. You can always find them there for water and some other limited fluids. And then if you have an interesting fluid that's not in your book, yeah, go ahead and use the internet. Question.
Yeah. Are you recording?
Recording? No. So I stopped the recording. Where is it? Now I'm recording. Good thing I have these other two cameras. Okay. Everybody can see the video on the PowerPoint. Good, good. Okay, so today what I hope to get to, pressure measurement datums, vapor pressure, and then surface tension is probably the last fluid property we'll be doing. So, most of you are familiar with elevations and elevation datums. So, we can have what we call a local datum, or we can have an absolute datum that is internationally or nationally or at a local jurisdiction recognized. So for example, there used to be the 1929 National Geodetic Vertical Datum. That was upgraded in 1988, so now it's the national datum that we use in Canada, the US, and Mexico is tied to the sea level up in Canada. It's a very specific location. And so you have an absolute elevation datum and you have a local datum. So for example, the floor in this room, if we just wanted to figure out the difference between the floor and the ceiling, we could take survey equipment, come in and put the survey staff on the floor and call that elevation 100. It's just a relative elevation, 100 feet. We shoot the rod on the floor, we shoot the rod on the ceiling. That would give us a different relative elevation. Let's say that was 120 feet. The difference between the two is 20 feet. If we had a USGS survey marker that was tied to the national datum, and we brought that elevation to this floor, the actual real elevation may be 67.29 feet national datum. And when we surveyed that, we would find that that would be 20 feet higher, but represented in the national data. So again, just as we have elevation datums, in which we can convert or go between the local datum and the datum set to mean sea level, vertical datum. If we had called this datum 0, when in fact it was really 100, we know that there's a conversion, 100 feet between the absolute datum and the local. And again, irrespective of the datum, changes in elevation between 2 points will always be the same. What's different is the number you use for the recording, whether it's a local datum or an absolute datum. So similarly, pressure has 2 datums. One is the absolute pressure, and the other is what we call a gauge pressure. Colloquially, that word gauge, perfect English from the Queen, would have a U in it. Within the last half century, engineers have dropped the U. I mean, you're not pronouncing it anyway, right? Gauge, G-A-G-E. So colloquially, you will see gauge written without the U. And the difference between the two is in an absolute pressure measurement datum, absolute pressure of 0 is a pure vacuum. Something you might have out in space. Pure vacuum is absolute 0. Whereas in a relativistic datum, what we typically do is 0 our gauges on local atmospheric pressure. So if we put that into a slide, again, we can have on the left-hand side an absolute pressure measurement datum, and on the right-hand side, a local or a relative or what's known as gauge pressure. When you go to the service station and fill up your tires, you're using a local pressure measurement datum. It's based on 0. And when you inflate your tires to 30 psi, that's 30 pounds per square inch above the local atmospheric pressure, which is set to 0 in that datum. So, on the left-hand side of this slide, you see an absolute pressure datum. 0, 14.7, 20 psi. Very commonly, around sea level, the atmospheric pressure is 14.7 psi, or at least that's what we will consider it to be. Is it always that value? Of course not. What that is representing is the weight per unit area of the atmosphere above. And that atmosphere above isn't always the same thickness, it changes. So the next time a hurricane or a low pressure front, as the name implies, comes through, that pressure can change dramatically, it decreases dramatically. On the weather at night, you'll see them talk about high pressure and low pressure. When you have high pressure, air is descending, and those are clear days, because the colder air above, as it warms and warms, just becomes drier and drier. Whereas when you have low pressures, air is rising. And so you have air at the warmest temperature of the ground surface with moisture, and as it rises and cools, you start to get the water vapor converting into liquid or ice. And that's where you typically get more cloudy conditions or even rain, low pressure systems. So you can see that in the absolute pressure measurement datum, there are no negative pressures. At least we haven't invented that yet, because you're working off of an absolute vacuum. Whereas if you zero your instruments and use a gauge pressure datum, if you zero your instruments to local atmospheric pressure, you can have negative pressures. Okay? But again, a difference between any two, for example, if you go from 14.7 and you have a little container that's at 20 psi, absolute. That's why the A is there, so that you know what measurement datum you're using. The difference between those two is 5.3 psi. If we subtract local atmospheric pressure from each of these values, subtracting local atmospheric pressure in an absolute sense from a pressure that's reading that, you get 0. 20 minus 14.7, 5.3. 0 minus 14.7, minus 14.7. And the difference is, in the old days, you would write PSIG. That means it's a gauge pressure. But since we conventionally almost always use that, and we like to be efficient, we just drop the G. So whenever you see the unit PSI, you know that's in gauge pressure. Whenever you see the units PSIA, you know that's an absolute pressure. And that means something. And it will come back to haunt us in later problems in this course. So that's what I wanted to start off with on pressure measurement data. So, the next fluid property I want to talk about is vapor pressure. And as with many of the other fluid properties we've talked about in here, vapor pressure is listed in the back of your book for water as well as some other liquids. But what is vapor pressure? Consider a container, and you'll see this in future slides. Consider you have a container. Let's try this out. It's closed, and you've got some liquid in there. So this is water, and this is just air. What's happening in this container is molecules of water are moving up into the airspace, and molecules of water vapor are moving down into the liquid space. That's what's happening. However, take a step back first. You have this container, you've set this system up, and now what you do is evacuate all the air. You create a pure vacuum instantaneously above that water. And what happens is water molecules do what they were doing before. They leave the liquid stage and they go up into the air stage. When you had the perfect vacuum, I just want to go back a slide. When you had the perfect vacuum, your pressure was 0 psia. When each air molecule enters that vacuum, it exerts a partial pressure in that space. Now you don't have zero pressure zero absolute pressure up there anymore. It's something more than that. And the more and more water molecules that were liquid that move up into the gaseous space create more and more pressure. So it goes from 0 to something higher. Ultimately, when the number of liquid molecules going to gas equals the number of gas molecules going to liquid, you've reached an equilibrium condition. And that pressure at that equilibrium condition is known as the vapor pressure. If you change temperature or pressure of the system, you will change that vapor pressure. So again, the vapor pressure is the pressure that molecules exert in the gaseous space. So again, this is what I indicated before. We're going to have this container, and we've got molecules going from gas to liquid, molecules going from liquid to gas, and ultimately they hit a balance. The first thing I want to describe, is the camera tracking me? No. Okay. So the first thing I want to describe is this upside down triangle on the left. That upside down triangle, you're going to see a lot in this course. It's a triangle, and then there's 1, 2, as many lines as you want under it. Normally I'll only put 1 or 2 lines under it. What that symbol indicates is an interface between two fluids. It could be oil and water, those are two liquids. It could be air and water, liquid gas. It could be two gases. But basically, the fluids are immiscible. So remember I brought in the toy with the little wave tank. It had an oil, another oil that was clear, blue, clear, and then air above it. And you could rock it back and forth, and that could give us an indication of immiscibility. But basically, between any two immiscible fluids, we just identify where the interface is. So you're going to see that a lot here. And then, as I discussed before, for these arrows going up and down, what's happening is that as particles go from the liquid up into the gas or the void space, they're exerting a pressure up there, and that ultimately reaches an equilibrium system. And that, at equilibrium, that would be the vapor pressure. So, as I said, pressure exerted by the vapor molecules in that evacuated airspace is vapor pressure, and we identify vapor pressure as P subscript V, and of course we could put a second subscript on that for the specific fluid we're talking about. So PV sub W could be for water, PV sub O could be oil. So, if you go to the back of your book, you can look up the very right-hand column, gives you vapor pressures. And if you went in there at 100 degrees C, you would see a vapor pressure of 101,300. And there are units at the top of those columns, at the top of that column. And those units I've reported here, 101,325 Newton per meter squared, absolute. That's the little a. That's telling you you're working in an absolute pressure measurement datum. If we wanted this pressure in a gauge pressure datum, we would subtract off local atmospheric pressure. If this is equal to local atmospheric pressure, basically the vapor pressure is 0. Typically, when does water boil? At 100 degrees C, 212. So you don't need any pressure. What you've done is created boiling by increasing temperature. Understand? However, you can get fluids to boil at temperatures of, say, 20 degrees C. In that case, you have to change pressure. And that's what we're going to talk about today and other examples in this class. So this is SI. This is our system of units. At 212 degrees Fahrenheit, you have this vapor pressure of 14.7 psi. The other way you could say that is the water would boil at 14.7 psia or 0 psi. And one issue, if you've moved around, when I lived in Colorado, things boiled at lower temperatures, and that's because you have less atmospheric pressure. And that changes how you do baking and a lot of other things if you pay attention to it. But again, in the Mile High City, at 5,000 feet, water boils at 203 degrees Celsius. You think, why am I going over this? Well, not everybody's going to work in New Hampshire. So if you go to work in a place like Denver, you have to be aware of these if you're designing, for example, a pumping system. You have to know when water's going to boil because you're going to be changing pressures in systems when you're moving fluids around, and you don't want to create this condition. So, the dark side of pressure, vapor pressure. What is critical when we're talking about vapor pressure is that we understand when it's an important aspect of our designs. So, for example, in water distribution systems, if we create pressures that are too low, the water will boil inside the pipe at ambient temperatures. So the water is 40 degrees Fahrenheit, but it's not liquid, it's gas. And once it turns to gas in the pipes, you have big problems. So if you've ever had a car that had problems with vapor lock, that's exactly what we're talking about. The gasoline between the tank and the carburetor has vaporized or turned to gas, and it basically stops the gasoline from moving anymore. If it gets into the fuel pump, then basically you've lost the prime of the fuel pump. Same thing happens in water distribution systems. If you get air building up in these systems because you volatilize the water, you can have the water completely stop, or you can dramatically increase pressures. Dramatically increase energy losses. So the other place, and I'll show you a picture, which is actually a video. You'll see it in ship impellers, pump impellers, siphon spillways. So what are we talking about? Basically, in these settings, even though the ambient pressure is well above boiling, we, by our design, has created a very localized area where the pressure is below the boiling point, below the vapor pressure. And so what happens is the fluid boils in that vicinity. So sometimes you'll hear of a process called cavitation. If you've ever taken a garden hose, and when it was flowing, you crimp the hose, and you hear the water moving inside, hissing at you, you are boiling that fluid. The hissing you hear are the air bubbles. And what happens is you created this zone where the pressure is below the vapor pressure, so all of a sudden you're boiling the fluid at ambient temperature. But later on, after that location, the pressure is superior to the vapor pressure. And then that gas collapses. And because of the very different density or specific volume of gas to a liquid, the bubbles typically collect on the surface, say the inside of the pipe or on the ship's propeller, and when it implodes, you're basically sandblasting that location. And if that happens continuously, you basically wear away the pipe or you wear away the metal. So in some of the ships that we were mass producing during World War II, after 6 months out at sea, ships' propellers, and these were enormous, almost the size of this room, they would come back almost paper thin because of the cavitation process. And obviously, it's happening around the edges or elsewhere. As that ship's propeller gets weaker or smaller, you can't thrust the ship as much anymore. So all of a sudden, where they could go 40 knots when they went out from dry dock, they come back and the maximum speed might only be 30 knots. Not good when you're trying to outrun the enemy. So this is a video that I've posted for you, and let's just see if it works.
If a propeller spins quickly, it leaves a trail of bubbles behind it.
So I'll let you listen to the video. But again, think of any underwater movie you've seen, and you see these bubbles around propellers or torpedoes, and everything's submerged. So where do those bubbles come from? What happens is, around the edge of this propeller, you've decreased the pressure to below vapor pressure. And so at ambient temperatures, that fluid's boiling, and the bubbles are what you see. If the bubbles were created, say, interior, and then as they moved out, they moved to a location where the pressure was above vapor pressure, that's where they would, at that location, implode. And again, that's how the propellers would be destroyed. So, here's a very simple example. Later on in the semester, we're going to see this in moving fluids, but I just want to get this concept to you. Here's our closed container, and in this closed container, we're going to have it in a piston system, a very tight fitting piston, and you've got water at 160 degrees Fahrenheit. The system's at equilibrium, and what we're going to do is lift up on this piston. That's going to create a vacuum here. And what we want to do is to try to estimate how much force we have to pull up on that piston to lower the pressure enough to equal or be lower than the vapor pressure to get the water to boil. That's the simple question. So again, if you look at this, we have atmospheric pressure on the top, and again, what's down here is the vapor pressure. And when we pull this up, what we're going to do is start reducing the pressure here. So, atmospheric pressure, I'm just giving it to you, 14.52 psia. If I look in the back of the book, the vapor pressure of water at 160 degrees Fahrenheit is 4.74 pounds per square inch absolute. Again, that's right from the back of your book. I'm just going to go back a slide. The force is being distributed over the area, the bottom area of the piston. So as we pull this up, that force, again, is distributed over the bottom. And that's what's giving us the pressure. So remember from the previous lecture, force is equal to pressure times area. Okay, so we're trying to figure out what the pressure condition is going to be or what force we have to pull to create a boiling condition here. So what's happening is we initially had atmospheric pressure here. By lifting up the piston, we want to create the vapor pressure of water at 160 degrees Fahrenheit. Initially, this was also at 14.52 psia. We want to lower it to 4.74 psia by pulling up on that piston. Okay. And so then when you flip back, what you have is a difference in pressure now across the piston. Atmospheric pressure on the top, vapor pressure on the bottom. The difference in pressure times the area of the piston is the force. The difference, the force is equal to the difference in pressure across the piston times the area. So, as I just stated in this equation, because the force is distributed over the piston area, that force is going to be the change in pressure, which is occurring from the top of the piston to what's below the piston. We're going to create the vapor pressure at a temperature of 160 degrees Fahrenheit. And again, we already looked that up. That's the 4.74 PSIA. And up here, we have the 14.52 PSIA. So again, that difference in pressure times the area of the piston itself is that force. So again, in the next line on the handout, the P atmospheric is the 14.52. The pressure inside is the vapor pressure. And then the area of the piston, we can just calculate pi r squared or pi over 4d squared. So to conclude, the difference in pressure, atmospheric pressure minus vapor pressure, 14.52 minus the 4.74 PSIA, and then the area of the, if we have a 6-inch radius piston, 12-inch diameter, the area is pi r squared. And I didn't convert it into feet because the pressure is already pounds per square inch. So pounds per square inch times inch squared is pounds. And that would give us a force of a little over half a ton, 1,100 pounds. So again, what we're going to do is have a system that was originally fine, minding its own business. We lowered the pressure on the fluid and made it boil. And unfortunately, that's what we do in transmission systems, moving fluids and piping systems, propellers, pumps, dam spillways. That's what happens. And so in the process of design, what you're doing is looking out for where that may happen and then trying to redesign the system so you avoid it. Okay, and if there's any questions, you're letting me know, and I don't see any questions in here, so great. So I'm going to talk about surface energy, surface tension and energy. So we've already introduced the fact that fluids that are immiscible don't readily mix. Now we can get them to mix just like the salad oil or the toy we brought in here by shaking them up. But right now we're not shaking them up, they're just minding their own business. And when we have two immiscible fluids, what happens is the interface between them is an interface in which you're trying to keep dissimilar particles, dissimilar molecules. So surface tension is particularly important when you have the two immiscible fluids and one of them, at least one of them, is in a very finite volume. So think of a bubble or a raindrop. In the first case, the bubble is in a large mass of water, but the bubble size is finite. In the second case, for the raindrop, the air is immense, an enormous volume of that fluid, but the raindrop is finite. So in those cases, that's where surface tension typically is going to be pretty important, and you will see it manifest itself. Surface tension is a fluid property that is directly a result of molecular attraction at an interface. And I mentioned here a gas-air interface, but it certainly can be at any liquid-liquid interface as well. And so what happens is, if we, how do we set this? So at this interface, because of molecular cohesion, for example, let's look at air over water. The water particles down below that interface don't feel surface tension. The water molecules at the interface really don't want to be there. They would rather be surrounded by other water molecules. Why? Because there's an immiscibility between these two fluids. They don't want to be next to each other. And therefore, there has to be an amount of energy to keep those molecules at the interface. And a measure of the energy needed to keep the molecules at the interface is surface tension. It's the amount of work or energy per unit of surface. So, again, what you have inside on this figure, inside the liquid, which is down below, think of air and water, you have molecules down below the surface who are surrounded by similar particles. Those at the surface are not. And the only way to keep those molecules at the surface is, again, some type of energy or force to keep them up there. So for finite fluid volumes, think again of the air bubble or the raindrop. For finite fluid volumes, that causes this surface energy, surface tension, causes the finite volume to deform from other than a plane surface. Again, think of the bubble and the raindrop. They're more or less spherical. Why? Because the sphere is the minimum surface area for a given volume. That's usually a calculus exercise.
You don't.
Yes.
We want you to stay on each slide a little bit longer so that we have time to write things down.
I will try to stay on slides a little longer, and I will also be posting these. And this is the heart of why the students didn't like the slides. And that, this is another, I'm glad this came out now. The question was, they'd like me to stay on the slides longer. Unfortunately, when I use this method, as an observer, you're not even able to scroll back and forth. Whereas when I use the blackboard, when you're in class, you can see all the blackboards, but even if you're not online, you can at least see a slice of the blackboard. You're able to keep up and look back. So that's the downside of using the slides. I'm aware of that. And again, next time I may just give the slides first. Again, we're trying this out, and you'll tell me which works better. So we talked about that. So again, work must be done to keep the finite fluid volumes particles at the interface. And this work is what's extending the surface or bringing other molecules to the surface if molecules at the surface leave the surface. Either they go into the other phase, a liquid water molecule goes into gas phase, or that's by Brownian motion, a particle of the surface moves down into the drop. So again, work must be done to keep the particles at the interface. And this work, again, makes the surface, that interface, act as a membrane. Membrane meaning it's all under tension forces. The work represented by keeping the particles at the interface is the free surface energy, or the potential energy. And what we typically do is divide that by just a unit surface area. So again, there is work to keep particles at the surface. And when we take that and divide by the unit area, or any unit area of surface, what we get is something with the dimensions of force per length. So surface tension is a measurement that has the dimensions of newtons per meter or pounds per foot. And in lab 2, you're going to be measuring surface tension. The magnitude of surface tension depends on the two fluids at the interface. Okay? And as engineers, we're capable of changing that surface tension. Typically, you hear about it using surfactants, right? So you can use something else to break up surface tension. Did anybody use surfactants today? So I already know you don't brush your teeth. Now I know you don't use soap to wash your hands. But soap is a surfactant that allows air and water to mix much easier. That's why you get the suds. That's a mixture of air and water. So in the oil patch, your first homework assignment, expect 2 more today. Your first homework assignment looked at hydraulic fracturing fluid. They use a lot of surfactants because they're going into a zone that has either gas or oil mixed with water. And they don't want separate fluids. They want them all to mix together just to pull them out of the well. And once they get them out of the well, then they can separate them. Okay, so although in most engineering applications, surface tensions are negligible, the forces are negligible, there are some locations or some engineering problems in which capillary action or surface tension is dominating what's happening. So one is capillary rise of liquids in narrow spaces. So for example, getting the water from the roots of a tree all the way up to the leaf. And you'll find that you can only raise water about 32 feet before it boils. You're going to find that. However, you can change water's properties so it can go up 100 feet without boiling. Add salts to it. So a tree sap is going to be affecting surface tension properties of liquids, water in this case, so that you can get the fluid going all the way to the top of the tree. Bubble formation, cavitation, we've already talked about. Breakup of liquid jets. So when you turn on your faucet at home, first you get a nice solid jet, and then it starts to break up into bubbles, or it breaks up. That's all due to surface tension forces. And when we do model studies, so if we're trying to look at the forces on a barge on the Mississippi River, you can certainly do full-scale modeling, but it's very expensive. Normally what we'll do is scale modeling. That's what's in Chase Hall. So the next time you're on the hallway, you'll see the wave tank, and then a big pool, which is a towing tank. And that towing tank is meant to do model studies. And when you do that, you can shrink the model scales down so much that all of a sudden, whereas surface tension is not an issue at the full scale model, it's a big problem in the scaled model. And you've introduced error that you may not account for. So remember chemistry. How many of you fondly remember test tubes, right? So here are two test tubes. The left one has mercury in it. Notice what the surface looks like compared to the one on the right, which is water, which is what you're more commonly used to seeing. So the reason why the meniscus is shaped one way or the other has everything to do with the characteristics of the three phases. One phase is the solid phase. It's a silicate material, glass, that's the test tube. The other phase that's common in both of those is the air above it. But the third phase that's different is the liquid. On the left is mercury, on the right is water. The water meniscus rises up on the surface of the test tube. Why? Because water wets and air doesn't. Given a preference, the water would be preferentially wetting or attached to the silicate surface over air. Conversely, with the mercury, the air wets and the mercury doesn't. Preferentially, the air would rather be next to the glass rather than the mercury. So again, the aspect we're looking at is we're going to take a little coupon, a little differential piece out of the surface on the right. And we're going to do an analysis on it. Why is that deflecting the way it is? Well, you have a finite volume of the water, and it's deflecting because you have two immiscible fluids, air and water, and a finite volume of one. So surface tension manifests itself by deflecting the surface into this meniscus. And I know you've all seen this. So again, what we're going to do is take a small coupon, and I may not finish this today, not the end of the world. So what we're going to do is look at down on the surface. We're looking down into the test tube on the right, and in that two-dimensional XY plane, what we see is a little coupon that's dx by dy in size. If we looked at the edge of the coupon, so if I looked at that edge, what you would see is that the edge is curved. Okay? And by taking the coupon away, what we're doing is recognizing how this little coupon knows that there's other fluid in that meniscus surface is it feels this tension or stress all along the edge. So that's what's operating all along the edge because we cut the coupon away from the rest of the meniscus. And so that's these forces that are happening in the x and y dimension. So again, you have surface tension times dy pulling on the left and the right, and the surface tension times dx pulling on the top and the bottom. And the other thing we'll notice is the radius of curvature in one dimension is going to be R2, and in the other dimension is going to be R1. So each of those has a radius of curvature, and actually, that's hard to measure. It's nothing you can see. What we want to do is relate it to the radius of the test tube. And we can do that through the algebra, because we're going to know or assume these angles, and we can get from the capital R's to the radius of the test tube. So that's what we're doing. We're taking a coupon from the surface. And question, I'm going to go back 2 slides. Is that meniscus on the right side, left sharp, right sharp, right sharp? So on the right sharp, right test tube, is it moving or is it just sitting there? If you turn away and turn back, are you going to see the same thing? So if it's not moving, it's steady state, right? Steady state system, Newton's first law, sum of forces equals 0. Depends on what we're analyzing, but that's what we're going to apply. Question?
Someone would like you to clarify what coupon is?
Coupon is just cutting away a little differential size piece of surface area. Not something you would use at Walmart. So again, we're going to look at the edge of this, and we're going to perform an analysis in the vertical direction. And so what we're going to hypothesize is that there's a difference in pressure. And I'm just going to zip back again. We're going to hypothesize that we have one pressure here and another pressure up here. That there's a difference in pressure, and they're both right at the interface. So when we go down to that, you'll see that difference in pressure here, and we're now capturing it here. And so if you think about it, PI is the atmospheric pressure, and PO is going to be the pressure in, say, the water right at the interface, but it's in the water, whereas PI is pressure in the air, but right at the interface. And so again, what we can do is look at the difference in pressures across the interface, and we're going to multiply it by the differential area. And that difference in pressure across the interface is due to the integration of the surface tension components acting in the z direction. That's the difference in pressures in the z direction. There's no weight to worry about because this is infinitesimally thin. So all we're doing is looking at the geometry and assuming that there is a pressure difference across this, and that the change in pressure times the surface area, that's the force here, would be equal to the sum of the surface tension forces the sigma dx, sigma dy forces that are acting on the edges. And we could be completely wrong. If there is no difference, I'm just going to go back a slide. If there is no difference across the interface, then there is no change in pressure across the interface, then surface tension is not an issue. Okay, so again, we're just making this assumption that we're trying to explain why is that interface curved. So again, we're defining these angles, and we're going to get rid of them. We want to put them in terms of things we can measure. These are very hard to measure. And again, the surface tension is only acting along the edges of this element, or this coupon, as I call it. So, we've got the pressure above, as we've already discussed, and we have pressure inside the fluid, but they're right at the interface. We're going to look at Newton's first law of vertical direction. So we're going to say that the sum of the forces in the z is 0. What are the forces? We have forces acting on the two edges in the y direction and the two edges in the z direction. But remember, because it's curved, those forces have a component in the xz and the yz. We're only looking at the components in the z direction. And so that's these forces. That's what's acting along the edges. and they're equal to that pressure force. So the pressure force, again, is the change in pressure dx dy. And so what we do is substitute in everything we can know or everything we're representing. Looking at this again, we can take these angles that we just assumed, alpha and beta, through the curvature of the surface and the radius of curvature. We can put those into terms of dx dy and the radii of curvature. So we can define alpha and beta in terms of the x dimension dx, the y dimension dy, and the radius of curvature. And when we do that into that last equation, this was ft, these were the sigma dy's, and there's 2 there because the coupon has 2 sides in the dy direction and 2 sides in the dx direction. So I know I went faster than this, but I'm giving you these slides. And I believe this derivation is in your lab and it's in your textbook. And I know you're doing the readings ahead of class, so you've already read this. I know, being so fast. So we can now reduce this. We can isolate the 2 pressures. We can divide everything by the area of the coupon, dx dy, the area of the element, and we get this next equation where the difference in pressure is the surface tension times the sum of the inverse of the 2 radii of curvature. If you have a sphere, the radii of curvature R1 and R2 are the same. If you have a jet, one of those radii are infinity, and the other is the radius of the jet. This is the equation that you're going to be using in lab. Basically, on the top of the test tube, you have half of a sphere. And in the lab, you're going to use a capillary tube. So that's the equation you're using in lab. And again, it's for a capillary tube. For a capillary tube, again, because you have a sphere, the 2 radii of curvature are R. And so again, this is the radius of curvature. And then that wetting angle is the angle between the fluid and the wall. And what we can do very quickly is we can put that radius of curvature in terms of the radius of the test tube. So in lab, you actually have the radius of the test tube. And ultimately what we do is we take that and we rearrange the equation, and this is the equation you're going to use in lab 2. We're going to measure everything but sigma, and you're going to calculate sigma. And I want to stop there. I know I'm over now. The classes go to 12:15, so the recording should not have stopped. But I'm going to stop here. I'm going to pick up 3 slides earlier on Monday. Okay? But I know I went faster than you. Any questions? I just want to say, 3 weeks ago, you can back up, 3 weeks ago, 50-50 chance we were not going to get to the first 2 weeks. That's what most people would say. So I'm impressed we made it this far. The next one is going to make it to the end of the month. So I think if we can do that, we're out of the woods. As far as we're doing things right, that doesn't mean this is going to go away or online's going to go away. It's just that we're doing things right. So I'm very impressed with students. Faculty is another matter. So you're right. There's nothing you can do about it. See you Monday.